talk about. So exercises are due when? Today?
A week.
A week from today? Next Tuesday? Okay, hopefully I'll get another exercise up. That will be the last one by next Tuesday. If not, then by next Thursday. Today I'm going to wrap up classical control, and it's, I think, the nicest class in classical control. This is called LQR, linear quadratic regulator. This is due to Kalman in the 60s. So this is a very beautiful topic, which almost completely nails down what linear control is about. Next Tuesday, I will start talking about the most exciting stuff, I believe, which is learning and prediction in dynamical systems, general dynamical systems, nonlinear ones, such as the LLM or the brain, and we'll be able to give rigorous theory about it. That's going to be very exciting. So this I'm going to start next Tuesday, and it will probably, how many weeks do we have until the end of the semester? 4? Sorry? 4. So 8 more lectures, kind of?
Except for the last week, we don't have. But you can,
oh, no lecture.
You're welcome to offer.
No, I'm good. Unless you, wait, last week there is no lectures?
The week before they
Okay, so 3 weeks. Why do you say? I mean, we end 22 lectures when? 3 weeks from today. Yeah? Okay, so 6 more lectures basically. Oh, okay, that will be 22, like 24 lectures, I guess. Yeah. Okay. Yeah, so we'll be able to finish. I think we'll be able to finish nonlinear prediction in dynamical systems or dynamical learning in general. Very exciting stuff. Some of it is not written anywhere. I'm updating the book, the textbook, second textbook of the course to have this material, and I just put another version online, which you can take a look. It contains some of the new material. And some of it, a lot of it, is based on the work of Anand, your TA, who's sitting here. And I have to keep updating the material because just some of it is not written anywhere. So it's a bit of an apology that some of the material is kind of changing. I mean, there is no clear textbook for that, and just because it's very recent research. But I think the textbook is in okay shape. I mean, it's rigorous. There might be some small mistakes here and there, but overall, I think it should be in decent shape. Which reminds me, I think I made a small, slight mistake on class. I mean, I think I had the right thing, but I might have written it a bit wrong, which is when we talk about stability of linear dynamical systems, the characterization of it, this was correct. So rho of A, which is the maximum magnitude of eigenvalue, remember that? And we said, okay, this is less than 1 if and only if the system is stable. And then I believe someone asked me, is it not, well, it means, basically, this means if rho of A is less than 1, this implies that for any x0, limit as t goes to infinity, a to the t x0 is 0. Yeah, you remember that? And I'm not sure if I mentioned that this can be non-monotone. Did I say it can be non-monotone? I did say. But did I explain why? That you can diagonal. So, well, basically the reason, it looks like it's monotone. That's what the intuition would have from the real valued case. But if you diagonalize A, it's U, D, U inverse. And these U's, you can, I assume the A is diagonalizable. Not always the case, but it's a dense set over the complex numbers. Where is Ellie? It's not here to kind of verify for me, but this is true. And then what happens is that this can be grown with time. So this D, when you raise A to the power, this D grows to the power. But these U's can be bigger than 1. So the U decreases, the D decreases monotonically, but the U's can blow up, at least in the beginning. So that's mathematically the explanation can be non-monotone. So it goes to 0, but it can be kind of go up and then down, the magnitude. Yeah.
But then we do know that once it reaches sort of a peak, it will then be monotonely decreasing, right?
I'm not sure this is the case. These are complex numbers.
So you could have
So you could rotate. You could rotate. I'm not sure that this is the case. It sounds reasonable, but yeah.
When you do it that way, it kind of makes sense to me, but like in the P set,
Yeah.
I would break down like x0 into like, let's say v1 to vm is like all the eigenvectors.
Yeah.
So you break it down into like c1, like v1 plus dot 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 like cn and vm.
Yeah.
And then every time you go through A, you add an eigenvalue to each of those vectors.
Yes.
And so isn't that like, since those values are greater, like less than 1 and it's to the power of t, isn't that monotonically decreasing?
That part is. That part is. But notice that there is a basis change. It's u, right?
Yeah.
And u is not orthonormal. If u was orthonormal, yeah, monotone. So for any normal matrix, this is called the normal matrix. If it's diagonalizable under an orthonormal transformation, so an orthonormal means that this u is 1, you know, they're all, and ui is orthogonal to uj. So if this holds, then yeah, everything is monotone. What you told me will work, because you can just basis transform the input vector and then apply what the argument you said.
Yeah.
But otherwise, they can blow up the x0. So x0 multiplies by this u inverse, it can blow up to something very large, and then it starts decreasing.
Okay, makes sense.
And that's an upper bound only. So to your answer, who asked me about David, asked me about monotonicity? You the one who asked? Maybe Edward. Edward asked me about monotonicity. Someone asked me about, I don't remember. But basically, there's just an upper bound, you can upper bound the norm of a times x0, and the upper bound initially can be very big, and it goes to 0, because the d to the power t goes to 0. But there is also a large number there that comes from the norm of u inverse and u. I think I did say it in class, now that I think of it, but I just want to make sure that I repeat it. Okay? Yeah? And then checking if a system is stabilizable, you basically have to check if it's stable, you need to check the rho, the largest eigenvalue. And that is by itself, it's not a trivial problem. You can write some kind of semi-definite program that does it. And I have it in the new kind of revised chapter of the book. So I wrote that, I simplified it. I have it in your version too, but I have a simplified version, which I will post. Questions about that? Okay. Anyways, so this was just a small digression because much of the material is in writing or new. The material, this is not new, this is old. The main topic I'm going to discuss today is called the LQR model. So again, we're dealing with linear dynamical systems. The reason we move to them, so linear dynamical systems are according to this equation. Xt plus 1 is axt plus but plus wt. This is noise. I'm going to assume that the expectation of wt is 0 for this lecture, so it's a 0 mean noise. It's not an adversarial noise. That's the LQR model, 0 mean. Let me also denote the expectation of wt transpose as big W. Suppose it's stationary, so the noise is always distributed according to the same mean and variance. Then X, this is the state. This is the system, these are the system matrices. And this is the input. And the reason we moved to this model was because we saw that polynomial dynamical systems are NP-hard, even if the degree is 4. Then we saw that we can discretize, we can move to the RL model. That's fine, we solved it. But it's inefficient modeling, we have too many states. And now we moved back to dynamical systems started from linear, as opposed to degree 4. Now the question is, the question of optimal control is the following question. I have a dynamical system, such as this one, or more generally, I can have xt plus 1 is f of xt ut wt in generality. Let's say now it's linear. And what I'd like to do is to minimize over all possible policies sum of costs according to the state and control. ut pi. So ut pi is a function of xt, pi of xt. Do you folks remember I talked about this problem when I just started talking about control and dynamical systems? Yeah? An example? Who wants to give? Yeah?
Sorry, so I just wanted to check that this means that the control process is Markovian in some sense?
It's absolutely Markovian because of this equation. So the state is determined by the previous state and previous inputs, and that's it. There is nothing else. And the cost is a function of the state and the control you take at this iteration. So all future evolution, it does not depend on previous states or previous controls, only on the current state. This already means it's Markovian, just like an MDP.
But I think I was asking the way you've written the control, ut of pi, you said it's some function of xt.
Of the state, yeah.
Of the current state.
Correct.
Okay.
And why is this the sufficient to consider, a sufficient solution? Why do I only need to care about the current state? Yeah?
Because it's Markovian.
Yeah, it's Markovian, right? From now on, all the evolution of the system forever and ever depend on the current state. So therefore, it suffices that I take action according to the current state to optimize it. Recall the Bellman equation we talked about. It's valid here too. Okay? This is a Markovian process. So this is the question, this is, I should say, expectation here, where expectation is taken over the noise, the random noise. This is a well-defined problem because I know, so if I know the dynamics and I know the cost functions, I can potentially compute it. I can compute the best policy. Everything is known. Everything I need to know are the dynamics and the state space, the control space, the cost functions. Is it clear that this is sufficient? I'm not saying efficient computation, but in principle there is a solution to this question. This was not true for all the questions we studied in this course. For example, prediction from expert advice, there was no way you could compute anything in advance. You didn't know what's going to happen the next iteration and so on. Here I know what's going to happen. It's predetermined. There is a physical system, it has costs. I can potentially compute the solution ahead of time. Is it clear? So in principle, this is a different kind of question we're asking here. On one hand, it's more complicated. On the other hand, it's simpler. So I have all information ahead of time, but I have dynamics that are potentially complicated and so forth. Yeah? So LQR is a special case of optimal control where I'm minimizing expectation of summation over T, xt transpose, we get the notation right, Q xt plus ut transpose R ut. So such that xt plus 1 evolves according to this. Linear dynamics. Yeah? Okay.
And here, Q and R are also indexed by time, or no?
They could be. I'm going to make them stationary for now. But they could be, and actually, everything I will say will apply very easily to the case that Q and R. So it's not going to be a big extension. It's a very simple thing to extend. They could depend on time. But, okay, important. A, B, Q, R are known ahead of time. They are known to the optimal controller, to the decision maker.
So just so I understand, the
Yeah, that's right. This is a quadratic cost. So it's a special case that in two ways it's special. First of all, the dynamics are linear, and in the second way it's special is that the cost functions are quadratic. What's an example for that kind of special case that we have talked about in class?
Reaching a destination with minimum force spent.
Very good. So you folks remember the double integrator. We had a car, we wanted to move car from source to destination, and apply the minimum amount of force or work. So force was u, then x was state was velocity and position, and that it affects, so the force affects the velocity by the Newton's equations, and that affects position by Newton equations, and the target is distance, maybe Euclidean distance, squared to the target. That exactly falls into the realm of LQR. Can anyone think of another case where this can be interesting? Well, maybe I will save slight. So important, it's important one. Important two. So this will generalizes to changing AT, BT, QT, RT, and known. So changing a known linear dynamics and quadratic losses. So now maybe someone can tell me where I can apply this at? It's actually with the changing linear dynamics, this becomes one of the most useful paradigms in all of reinforcement learning and control. I wonder if you can see why that is. Anyone here doing robotics at all? Yeah? You are doing robotics? Did you hear of model predictive control? Okay. So any connection that you see here to MPC?
Easy. Like, let's say you're trying to like program a self-driving car in a changing environment. Like I couldn't like specifically tell you where the A, B, and Q are would map, but like I'm kind of starting to picture it.
Well, let's forget about the Q and the R for now. That's just some cost, you know, we can try to think, maybe quadratic. I should say, I can have known, and also I can add linear costs. If I want, that's also okay. So linear costs, maybe they're always kind of okay. I can take any convex cost and take the gradient approximation. It's fine, right? And linear dynamics, it's changing. So I can take any nonlinear dynamics, for example. I can take a nonlinear dynamical system and then approximate it by the Jacobian, by linearization. That will be linear dynamics. It's changing, because if I move to another point, it's going to change to another linear dynamics. But that's fine. I'm now telling you that this is fine. I can handle that. Okay? So I can take any nonlinear dynamics, if I know what it is, take the Jacobian approximation, and do it over maybe several steps, see what kind of trajectory it rises, take the linearization there, apply the LQR, solve it, repeat, and do it again and again. I will repeat what I'm saying now at the end of the class. But this is a very important paradigm. It's called model predictive control. The algorithm I just told you is called ILQR. There are various other algorithms related to it. Basically, that's the workhorse of any of the self-driving cars, any of the robots that you are familiar with. Questions? Yeah.
Sorry, not to get too hung up on notation, but you wrote such that xt plus 1, or that such that x goes to xt plus
No, this is star. Star is that equation over there. So it behaves like this, linear dynamical system, LDS. Yeah, that's fine.
I'm just a little, because when I see a such that, when I see a min and then such that, I'm thinking of it as like a constraint.
Well, it is a constraint. So the constraint is that xt plus 1 is equal to axt plus but plus wt.
Oh, okay.
Okay, so it is a constraint. That's how the x evolves.
Okay.
He has to evolve like that. And I want to minimize this. Minimize over basically u1 to u2.
Yeah.
Okay?
Yeah.
Yeah, Kia?
I have two questions. One, do we assume anything about the structure of Q and R? Like, I would assume you say R is maybe positive definite.
Oh, absolutely. Yeah, that's a good point. If R is not positive semi-definite, the function is not convex. So we don't even know how to solve it without the constraint. And in fact, I proved it to you in class, right? So we said the quadratic optimization problem is hard, even if there is no dynamics. We reduce from max cut. Very good point. So Q R are positive definite. So I denote it like this. So all the eigenvalues are non-negative, so the costs are convex. I mean, if they're not convex, we're in trouble. Even without dynamics, they're in trouble.
Wouldn't you want Q to be only semi-definite? Because, like, for example, if I have a car, like, if I'm parked, there should be no cost to this. Like, there should be states that you don't incur cost.
I think what I say will apply to that, but just to be safe, I'm making it bigger, strictly bigger than. You can make it bigger than epsilon, so epsilon can be very small. So the strictly bigger than is not really a big constraint, right? So maybe we have a tiny cost. You don't want to park forever. Okay. Yeah. Yeah?
You could also have that B0 cost if you were trying to park somewhere, if you add linear, right?
Hmm.
So like if you want to have xt minus target,
Yeah.
identity xt minus target,
Yep.
then you can get there just by adding linear terms. So you need to do, like, you have some xt dot target terms as well.
I guess you can always take the gradient approximation. Is this what you're saying? Always take the gradient approximation. If the interval between time is very small, that's a good approximation. Yeah. If you have a convex function, that is true. You can do a gradient approximation too.
I have one more question.
Mhm.
So model predictive control, you predict like a few steps out, and then you only do the next step, right? And
Yeah,
you
correct.
just keep doing that.
Correct.
So do we assume linear dynamics, or do we just like?
No, no. So I didn't write anything down, if you notice, because I'm beginning it very shallowly. I can describe it more in depth at the end of after I prove what I want to prove. But the idea is what I will tell you is a very good paradigm that completely solves this kind of special case I'm talking about. And because it solves it so well, we can use it in more sophisticated heuristics that don't have any theoretical guarantee, but it will be used in that heuristics. So at the point that you have nonlinear dynamics, there is no theoretical guarantee even possible, but you can still use these heuristics, as I will show. Okay. And they work extremely well. They work extremely well. So even though at that point, theory is a bit gone.
Wait, so you're saying this will still work if your nonlinear function is not convex? Like,
The cost, you mean?
no, you're like, I guess
The dynamics.
Your dynamics, yeah.
Yeah.
Okay.
That's what the robotics people do. They don't really know what to do. So they take any tool you give them and apply it. And this is a really good tool from the 60s. And you can apply it because robotics in general is very hard. You have all these nonlinear polynomials in there. And even worse, trigonometric functions and so on. And then theory is gone in general. And you have to apply all sorts of approximations. And this is a very good approximation to what's going on. But at least I motivated you. I mean, let me again say the model. It seems like you guys are interested in model predictive control. Let me say briefly what that is. I have a dynamics model. So I know my car, my airplane, whatever it is. Now, it's hard to solve. So what I can do is I can approximate it by linear dynamics, locally. Locally, it's linear. Everything is as long as it's smooth. And then I can use LQR to solve it, take a step, and recurse. Okay, makes sense? So it's an iterative linear approximation where the linear approximation is done by LQR. Good. More questions? Yeah.
So you said the linear approximation is done by LQR?
Solving the linear approximation.
Yeah, choosing the control.
Yeah, the linear approximation is done by Taylor series.
Yeah.
So you take a nonlinear function, you take the Jacobian, it's linear. Right? Because for even if I have a nonlinear dynamics like this, I can write it like the following. I can write f of some x bar u bar for as long as it's a smooth function plus Jacobian with respect to x times x minus xt plus Jacobian with respect to u minus ut plus more things that are second order. Yeah? Now what is this? I can call this AT, I can call this BT, and voila, I have an LQR problem. That's roughly what I can do. Make sense? Yep. Okay. So with this in mind, so this motivates why this problem is important. I think it's important anyways, just by itself is interesting, right? I mean, we don't know how to solve anything pretty much, except by value iteration, which is not an impractical algorithm. It works over all the entire state space that's too large. So this is the first thing I'm basically showing you how to solve, but solving efficiently. This is the first efficient algorithm, and pretty much the only one that we know. There are now a few more recent ones, but it's going to be an efficient algorithm. Now, okay, so let me state the theorem, which I think is surprising. An LQR problem, which is given by A, B, Q, and R. Again, I can generalize this to with subscript T. Forget the T for now. Let's say over T iterations, I can extend it to infinite. Can be solved efficiently. The solution is a sequence of linear policies. Which I'm going to denote by K1 up to KT. So this means that the UT I'm going to play is going to be KT XT. Okay? That's how the solution is going to look like. So look, a linear policy of the current state. Yeah, that's the theory. I think it's very surprising. Yeah?
And this gives you the exact minimum.
I will tell you. I will tell you the exact. I will tell you the exact how to compute it and what the exact form of these Ks are. Okay? But they're computable from A, B, Q, and R. Is it clear what I wrote? Maybe it's not immediately clear why I'm saying it's linear policy, but think about it for a minute. Why does it have to be linear? I mean, I have a problem. It's a structural problem. I have an NDP over infinitely many states. So in theory, a policy can be map any x to any u. doesn't have to be linear, it doesn't have to need any structure at all. Right? In principle. Doesn't have to be linear. So, but I'm saying it's linear. And I'm saying that I can compute it efficiently. So this is a surprising thing. Okay? Questions? Is it clear why I'm saying it's surprising? That's kind of what I hope to get across, yeah?
Yeah, I mean, I'm surprised by it.
Okay,
At
good.
least, like, I'm very curious. I'm not so shocked that it's linear. I mean, I'm not sure why it's linear, but I'm curious about this efficiency claim. Because if you ask me about this problem, I would say, I'm probably going to need to do some approximation at some point. Get an approximately good series of controls to,
Yeah.
you know, with some probability or with
Yeah.
some bounds, do close to the.
Yeah.
That's what I would expect. So that's where it's surprising to me that you could get it exactly and not by approximating the sequence of controls.
Yeah. Okay. I agree, and I think. I hope. To me, the most surprising thing is that it's linear, right? I mean, now that I know it, it's not so surprising. But if I were to not know it, try to imagine myself not knowing it, why is it linear? This doesn't make any sense. Why is it not some ReLU? I mean, who knows what it is? It can be like anything. Yeah, Angelos?
So KT can be any matrix, right?
Yeah.
Or,
Yeah.
so if you, just maybe this is a stupid question, but if like, let's say I have optimal control U1, U2, UT,
Yeah.
and like, can I not always find like a matrix K that satisfies KT times X is UT?
Yeah, but that's not a policy, right? It's not a policy, what you're telling me. You'll find a sequence of U's. And
Yeah, so if I find a sequence of U's, I can always find matrix K such that Kx equals 0. Am I missing something?
it's not clear. The U's will depend for different noise instantiations. You need to know this ahead of time, okay? Okay, this is a good question you're asking. My boy is doing a tour of Princeton right now, but fortunately I cannot answer him. Where was I? You're asking about use. Okay, let's think about the setting of optimal control again. Okay, optimal control. We have all these. So this is how it is. I need to set in advance all the everything. I need to solve it, right? Everything is known ahead of time. If you give me a set of U's, what if the trajectory there was some noise and push me to the side? You're still going to, it could be that I'm trying to move the car to some place, and then the noise push me forward. I need to do something else. So it has to be dependent on the current state. It can't be a fixed set of U's, right? We're talking about a Markovian system. The optimal action depends on the state. It's not an independent of the state. So U's, you're right, for any U I can find a matrix. But I need a policy mapping X to U. And that mapping is not clear that it's linear. It's not a single U. Does it make sense what I said right now? Okay, this was a very important point. More questions? Yeah, Kara?
So do we have to say what our policy is before we see the noise? Or
You can see the noise, that's fine. But the policy doesn't have to depend. The policy, so the optimal solution, what is the solution? This is how the problem is phrased. I know the dynamics, I know the costs, and now you need to tell me what the solution is. It's a policy. Mapping states to action, okay? So Markovianity says, doesn't matter what the noises were, you're at a certain state, now map it to an action. You want to give me a more complicated policy, that's fine, you're allowed to do that. I'm telling you, you don't need to. In theory, you don't need to, and also the solution doesn't need to. Let me say one more thing here. If t goes to infinity, then kt equals k for all t. There is a single k, a single linear policy that's optimal. So when this actually approaches exponentially fast. So basically, there is a single linear map from state to action that solves the whole problem. It's non-standard for me. I'm going to check on my boy. 1 second, okay? I'm sorry for doing that. He has to get into Princeton, so. הכל טוב, אני מלמד. טוב, ביי. Okay, good. No emergency. Sorry about that. Yeah, Edward?
I'm sorry, it's not very clear to me why if t is finite, then we need the time varying policy.
You will see that. You will see that, yeah. I guess it is not very clear right now. I agree with you. I don't have a good answer for you, but in the proof you will see. But maybe as t goes to infinity, it's kind of clear it's going to be the same, right? There is no asymmetry, right? But you can see maybe for when I want to move the car from one location to the next to another one, maybe I want to push a bit stronger in the beginning, weaker in the end. I don't know. It depends kind of on various time potentially, right? Because it's quadratic function, so maybe it depends on time. There was another question here. Okay. I should say, this is also a very nice structural result. So the fact that I can solve it ahead of time and come up with a linear policy, you can see how useful that is for things like MPC, like model predictive control. Because you have a succinct characterization of the solution. It's not only you can solve it efficiently, okay, here, over here, the robotics, yeah? You see that it's also a succinct characterization. So I have a matrix that kind of captures everything, which is good for a book. Extremely practical, extremely practical. This is used all over the place. And I can say it's a wonderful result. It's not mine, it's Kalman's, so I can show off, you know what I mean? It's a wonderful result, and it's extremely practical, and it's used in robotics all over the place. Those of you who have, you're in robotics, you haven't seen this LQR, MPC, ILQR, you know what I'm talking about? Yeah, so these are very well-used algorithms, very common algorithms. Yeah?
I mean, this is a silly question, but based off of what you were just saying, why is robotics still hard?
I'm glad you guys are asking me these questions. So, in what I've described, there are no constraints. This means I can give you, for example, infinite force in some direction. Suppose I want to move, I have a pendulum that I want to move to be upright. If I'm allowed to use infinite force, okay, and then leave it there, okay? So, but that's not the case. Maybe you cannot use infinite force. You have to use some small torque, or you have various constraints, and then you have to maybe push it here, then again push it here, it's going to go higher, then again push it here, and kind of use the momentum to allow it until you can actually reach it up. And those of you who plays with Mujuku and other, you have a remark?
Yeah, I was just going to ask, like, if your additional constraint is to minimize force, is that captured in either Q and R beforehand? Or no?
Yeah, just identity. So,
Okay.
just identity. So, distance to something, by Euclidean distance is Q is identity, and then force is just identity also. So, some integral over the force over time is called work, or energy, or I forget what. It's energy or Anthony, I don't know, you will tell me. Some energy or work, some kind of quantity like that, yeah? Which is what you want to minimize. Yeah. Some other question here? Yeah?
There's a notion of like not being able to use infinite force. Like there's going to be some instability at the top, so you have to precisely force this and precisely force this up, so you can't keep the system stable. Whereas infinite force, you just kind of like.
But when it's at the top, you don't need a lot of force. You kind of need a little bit of force to keep it there. I think that's fine. Kind of usually the difficulty is when you're here, you can't really tell, you can't really do that. So you have to like, in these Mujuku environments, you give it a little bit of force to go here, then it starts going back, you give it a bit more, and it keeps oscillating more and more and more until eventually it turns here. And that's the hard part, that's the planning part that is usually hard for these control algorithms. The same is true for mountain car, there are various other environments that you might see in Mujoko, and the constraints, who asked me that question? That was a very good question. You asked me? Very good question. So that's what makes it hard usually. You have a constraint, the environment changes, another thing. So here I'm assuming I know ABC, ABQ. Why would I know them? I have some robot, I don't know anything about it. Okay? I don't know anything. All I get is a visual input. So the input's going to be different. I don't know the actuator properties. I don't know definitely it's not linear. So there are all these other factors that make it much more difficult. Nevertheless, it's a very good paradigm, sub-paradigm for special cases. I will talk about unknown systems, partial observation, starting next week, but not today. Today, full observation and kind of the easy, let's wrap up classical control first. Okay? More questions? That was a very good question. Yeah. So let's prove. And the way I'm going to prove it is I'm going to argue about the value function. And that's something maybe you remember it from last week, but maybe it doesn't immediately sink in because I'm talking about control, not about array. But it is a Markov decision process. I can argue about the value function. And I claim, so value function at time t, for every state x, is quadratic. With this basically equal x transpose stx plus ct. That's the claim, with st being positive semi-definite. Okay, is the claim okay? Again, no reason why the value function has to be quadratic. Just a value, the Simon's value, which is the infinite horizon cost, in this case finite, if I have finite time, from one point until the end of time, and there is no reason for this to have any structure at all. We didn't have any structure when we talked about reinforcement learning. It was a value, and we wrote the Bellman equation for it. Right? I'm going to do the same thing here. I'm going to write the Bellman equation. But values will define. It's over infinitely many vectors. Fine. It's well defined. I claim it has a special structure, quadratic structure. Jerry, what's bothering you?
I'm just trying to understand why it would be quadratic.
Ah.
Yeah, I don't know.
Yeah. It comes from the costs. So I will show you. Costs in the Bellman equation. Yeah, Arnav?
Sorry, how is that supposed to value function back here with like A, B, Q naught?
Oh, you remember value function we defined in reinforcement learning?
Yeah.
Value means if I start at a certain state, what's going to be my expected reward from now until the end of time, according to the dynamics and the costs that I have. So the dynamics are what I wrote there. The costs are what I wrote there also, over there. And infinite horizon reward, expected infinite horizon reward starting from the state.
It's like this with like UT, like 0 hours, like knowing, but like just value.
No, so I don't need the UT. So, right. So I do. This is true. I don't need the policy. So value function will define with respect to a policy. You're right. Yeah. So this is the optimal value function. So optimal value function. I defined that. Right. So you're right. I needed this additional word. It's for the optimal policy. So UT is played according to the optimal policy. Then it's quadratic.
How are we dividing the rewards from the cost?
Same thing. So
Is it just negative?
yeah, negative. Yeah, same thing. I kind of use interchangeably reward, loss, minimize, maximize, convex, concave, because it's hard for me to keep track. But you guys know what I mean. So every time something is reward, I want to maximize, it's concave. If it's loss, it's convex, I want to minimize. Okay? You guys are okay with that, right? I hope. Yeah.
So, just to be clear, are we in the infinite time horizon or the finite?
No, finite time. Finite time.
Okay, so then the optimal is with respect to this sequence of policies? Because you...
Yeah, so optimal sequence of policies, yeah. Yeah, Jerry?
So it seems to me like if I accept that, then it makes sense why it would be like quadratic. Because I guess if you plug that in there, it's like quadratic.
Yeah, that's right.
And you also need quadratic for that to be like. I mean, you can't just. I guess.
What you're saying is exactly correct. which motivates what kind of proof? You're right. You're exactly right.
Do you like unroll it from the?
Yeah,
from the-
exactly right. So I'm going to prove by backward induction, okay? That's how I'm going to prove it. By basically induction. Okay? So proof by induction. And I go from t backward to 0. So what is the inductive claim? Inductive claim is that optimal value function is quadratic and optimal policy is linear. This is the claim. Okay? So let's look at the value function t x at time t. Okay? What is the value function? I'm going to write the Bellman equation. Well, what is it? There is no more future. There is just instantaneous thing I'm going to pay, and next state is irrelevant completely, right? Let's write what it is. This is equal to minimize over all policies or u's, and I have here the cost. So it's x transpose qx plus u transpose ru plus value of t plus 1 of the next state. But this is 0. There is no next state. Doesn't matter what will happen next time. So what's the optimal thing to do? 0, obviously, right? Okay. So then u star at t is 0, k t is 0, and then vt of x is equal to x transpose qx. So it is a quadratic. Yeah, Jeff?
It's not obvious to me why you would do that, because is there not a case where
Well, there is no future state. So the x I'm paying now, the u I'm paying now, and I'm not going to ever pay anything else ever again. So I don't want to pay anything. It just doesn't matter what will happen tomorrow, right? Yeah? Good. Let's do the induction step. So what do I assume? I assume that Vt of x, Vt plus 1 of x, is equal to x transpose St plus 1 x plus Ct plus 1. That's what I assume. And I want to write now the value function, and I have also a linear, the optimal policies are all linear from that point on and so forth. And I want to prove that the optimal policy at the tth iteration is linear, and that the value at the tth iteration is linear also, is quadratic also. That's what I want to prove. Questions? Yeah, Kia?
you also make an assumption for the inductor stuff that the policy is linear?
I don't need that. I don't think I need that. I mean, I could put it in, but I don't think I need that. Let's see. I don't think I need that. Yeah. So, is it clear what I want to prove, though, right? Let's write the value function at time t. That's equal to the minimum over u. T. And I have xt transpose uxt plus ut transpose rut plus value at time t plus 1 of x at time t plus 1. Yeah, everyone agrees? Okay. U. Let's keep u as variable. Now, value at t plus 1 of xt plus 1, it's a quadratic. So that's equal to mean u plus u transpose RU plus, here I have a quadratic, it's xt plus 1 times st plus 1 times xt plus 1. But what is xt plus 1? I know what it is also. So it's equal to a xt plus b u transpose st plus 1 a xt plus b u there is actually plus here there is plus wt, and I can take expectation over the whole thing. I'm going to, let me do noiseless. It's a kind of another term that's annoying to me, but I'm going to ignore it. You can add it if you want. So if I want to add noise, I'll take expectation over the w, which the linear term over the w is going to cancel. It's zero mean. There is a quadratic term. It will come into the constant. Okay? Plus a constant, plus ct. Everyone okay so far? Yeah?
Yes, you probably want to write dt of xt, no?
I want to write
dt of xt plus mean u in the first line.
yeah
dt of xt, bt on the left.
of
No, on the left was the first thing in the line.
oh yeah VTO. Well yeah, it's true for any x, but yeah. More questions? I guess xt is a variable. I should have just tried it.
Yeah, you either delete the subscript or.
Yeah. Let me leave it for now, see if I need it. I don't think I need it, but yeah. Okay? So, good. Well, this is already, you know what, let me remove the subscript xt because I want to prove xt. Yeah. Okay. Now, first of all, first thing you can see is that it remains a quadratic in x, right? Well, but again, depends on the u. So let me first see what is the optimal u here. What is the optimal u? I have a quadratic. How can I figure out what the u star is to minimize this thing? Et voila, good. Set the gradient to 0, right? So it's a quadratic function. Here is where I need positive definiteness, not semi-definiteness, because I want to have a unique solution. I think some things can be said even without it, but for simplicity. So when is this optimal? As a function of u, it's a converse quadratic. So let's take gradient with respect to u and equate it to 0 of what's written in here. This thing disappears. I have Ru plus this thing. So here I have something like st plus 1 times ax plus b u. Let me be precise so I don't make a mistake. But I'm going to have some linear function of u. It's not going to be super linear. I started with a quadratic, going to remain linear. So the gradient turns out to be the following. I have 2 times r plus b st plus 1 b u plus 2b st plus 1a x. So let's see if that's true. So I have u multiplying the axs, that's what I have here, and I have two of these, right? One from this u, and another one from this u. And then I have a u squared coming in for multiplying r, two of these, and I have another u squared multiplying the bsb. Yeah? So that's what I have here. So this means that u star equals what? Equals the following. It's the inverse of this 2r plus b st plus 1b times 2b st plus 1a times x. And what I can do is call this thing k. This is kt times x. Yep. And where's the minus?
Because you moved the BAST plus 1AX.
Yeah. I think there's a minus here, right? Like this. Yeah, you're right. Yeah. So therefore, here.
He's asking how the order is an inverse, but it follows.
Oh, okay. That's a good question. Well, R is positive semi-definite, right? Positive definite, sorry, positive definite. Now, I have here st plus 1 also positive semi-definite by induction. And when I multiply by the same matrix from both sides, it remains positive semi-definite. So the whole thing positive semi-definite plus positive definite is positive definite, and that has an inverse. Okay. So kt, I got kt times x. So this means optimally nu is ktx. U is a function of x. That's already good. Now let's look at the value. Let's plug that back in. So therefore, less u. So v of x, I have here minimum over u. I can plug in what the minimum u. I know what it is. So now I have, it's x transpose rq. X plus x transpose kt transpose rkt x plus the rest of the stuff there. So I have ax plus bkt x transpose st plus 1, again, a plus bkt x, which is equal to x transpose st x. Quadratic. I define st to be this big matrix. Okay, so st equals q plus kt r kt plus da 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 da. Sum recurrence of the equation, and I get a quadratic. Now this is PSD. Since st plus 1 is PSD. Okay, so st is PSD, and I can continue the induction. Yeah?
This doesn't matter that much, but ST could be PT, right? Because like in the very beginning, that's just Q.
First of all, this is also true, even if it's PD. Second of all, it's not, if I assume Q is PD, yeah? I think you're asking if Q is allowed to be PSD, and I think the answer is yes because of this observation by Charlie, right? So I think this is correct. So if Q is PSD, this will remain PSD. If it's PD, it's PD, and so on. Actually, I need it to be PD, I believe. Oh, okay. So it's PD. And the reason is I do need Q to be PD because I use that in the induction to derive a unique optimum. So for every single unique optimum, I need it to be positive definite, not positive semi-definite.
But
I can relax it. Yeah, you're right. Yeah, it looks okay. Looks like I can relax it to positive semi-definite. It seems to be the Q can be positive semi-definite. It's still okay. Questions? Yeah, that's it. So this ends the proof. So I proved to you that the value function is a quadratic and that the optimal policy is linear. Yeah?
So this makes sense already finite. You claim that this holds for like t equals 1.
Yeah.
How do you balance it?
You need to argue on the limit that these things converge. So you have a fixed point equation, basically, what happens in the limit. So what I wrote here, writing, actually it comes from this equation. So ST equals this, plus, let me write it explicitly what it is. I have here A plus BK transpose ST plus 1, A plus BK. Right? And this gives you an equation which is called it's a very interesting equation. It's the Riccati equation, discrete. It's called the DARE. Which stands for discrete something Riccati equation, discrete algebraic Riccati equation. It's one of the most well-studied equations in science. And it goes like this. So if I take the fixed point equation here, it's going to be S no t equals Q plus K RK plus A plus BK S A plus BK. And you can show that this has a solution, a unique solution under some conditions, such as positive semi-definiteness and so on. And then by that fact, you have basically shown that even in the infinite horizon, you have a quadratic value function, a optimal linear policy, and they're consistent with each other. So therefore, they are a solution to the Bellman equation, and therefore it's the solution, the infinite horizon optimality. It satisfies the Bellman equation, optimality equation, therefore it's optimal.
So first you argue the existence and non-existence of fixed point.
Yeah. Yes, yes. And the uniqueness and existence follows from positive semi-definiteness of Q and R. So that was a good question. Yeah?
Could you explain why the Dare equation holds when you get rid of the subscript t and keep the square?
Well, that's how you derive it. I didn't say why it has a unique and it exists and has a unique solution, but you can prove that, which is beyond my scope, but you can prove that. Basically, what you can show is that there is a contraction happening here between ST and ST plus 1. And then in the limit, that contraction becomes an identity.
Oh,
Okay? But I didn't show that here. It's a misleadingly complicated equation, honestly. This is a quadratic kind of equation and not trivial. Good. I should say, the k, this k, by itself here, it has two variables in this equation. When I plug in this k, that's when I get an equation only in S. There is no more k. Okay? Yeah.
Clarification. So in KRK, is the first k k or k transpose?
Transpose. But let's get back from infinite horizon to finite horizon. I think it's easier to reason about that. So finite horizon, I proved to you pretty much everything. I didn't leave anything unproved. So optimal value function is quadratic. Optimal policy is linear. You can solve for it. And remarks. So one, it generalizes to Qt and RT. If they change over time, You all see that there is absolutely no problem with that, right? Everyone agrees? Yeah, no problem at all with QTRT. So, generalize to AT BT. You all agree that if AT and BT change over time, that's also not a problem at all? No? Don't agree or agree?
No, I mean,
It's okay, yeah, okay. Yeah, everyone okay with that? There is nothing in the equations that should change. It's just that I didn't want to bother with the subscripts. But everything's going to be exactly the same. What else? It's efficient. Yeah, there is nothing here but convex kind of manipulations and simple algebraic manipulations, quadratic time potentially. So it's efficient. Four can add linear terms. Everyone agrees that I can add linear terms and nothing will change at all. So linear, the gradient is not going to change by more than a constant. Everything here is robust to change the gradient with up to a constant. Yeah.
So the efficient algorithm we have is we like have to start from like t equals capital T and induct downward. Like if we're trying to find an efficient solution where t goes to infinity, like does that make sense?
Yes. What would you do? I'm asking you. How would you solve the infinite horizon discrete algebraic Riccati equation, which is a fancy name, for something not that complicated? How would you solve it? Jerry, how would you solve it?
I don't know, I feel like you can just set t to be large and see like if it converges.
Okay, but look, that's not very efficient. You need to do the whole t computation and stuff. Wants to tell me? Arnav?
Do we just hope that people have found efficient ways of solving like that?
They did, but I'm asking you guys. I didn't think they did a great thing. I mean, there's better ways to. You can do a simple thing, which works.
I guess if you want k to be clear, hoping that k is 6, then we can just do it forward step and minimize it.
Good. I mean, I can do recursively, right? I can just recursively update. Take some s and k, like value iteration, but iterate on the s and the k. And then keep on computing the st plus 1 and the kt plus 1 from them and kind of hope that it will converge. And it does converge extremely rapidly. Okay. So, yeah, that's what I would do. And it works. It's quadratic time. It's not that efficient, but it's fine. Then, how would you use this as a building block for more complicated control? Let's say I have nonlinear control. I started talking about this MPC, right? So let me give you kind of a template for MPC. I should say this is pretty advanced material for robotics/MAE kind of courses. Many times they'll do a whole course, by the end of it reach this thing. But I think I gave you the essence, the most important aspect of it. So, okay, let's MPC, model predictive control. So I have a model. A model means that I know when Jan LeCun is going to talk about world models on Tuesday, what it means is that you have some kind of way of predicting the next state from the current state and the input, and maybe the perturbation, or usually the perturbation is zero mean. So you have some kind of function that you can apply. Now, what can I do? I can say the following. Okay, I started some x0, I don't know, or maybe I know what it is, maybe it's 0. And what I can do is I can say at my current state, let's linearize. So xt plus 1 is going to be Jacobian with respect to x minus xt, plus Jacobian with respect to u minus ut, plus little order of 1. So something that we hope goes to 0 because it's a very small. And I call this A and I call this B, T. And then I can write, this will give me xt plus 1. Now I can write xt plus 2 to be same thing. And I can do it for maybe for 10 iterations. So I will get x1 up to, so xt up to xt plus 10, and a t bt up to at plus 10, vt plus 10. Now, I'm going to solve LQR on these matrices and play K1 and then repeat. Again, linearize for 10 steps, solve, play x1, play K1, and do it again and again and again. And you can, mix and match. Maybe I will play 5 iterations, discretize for 20, give your favorite hyperparameters. It's called model predictive control. My model will predict into the future. Maybe it doesn't predict great. So for example, this linearization that I do, maybe I need to change it. Maybe I need several iterations of, well, I'm linearizing. All of a sudden, I solve, I get some other points. So I need to linearize again. You might want to do that until you converge, okay? Because these are not fixed, right? They depend on your location. And you do that a few iterations, play the poles that you found, repeat again and again and again. So this is extremely useful. Very, very widely used. Can be applied to any nonlinear control problem. And it works many times. The downsides of it are that you need to solve from scratch pretty much every iteration. You don't have a fixed policy. So this is not a fixed policy. It's a fixed control, but it's a control algorithm, but it's not a policy. You don't get like a neural net that tells you what to do with every location. And in that sense, it's kind of slow in real time. Many times real time, it's not extremely fast. Nevertheless, this kind of technique has been extremely widely used all over robotics. Questions? Yeah?
Is the first time step the best approximation?
Yeah, because at that point, you didn't move anywhere, and your linear approximation to the nonlinear function is good, is reasonable. Once you move to the next step, you do a linear approximation over there, but you're not even sure that you're taking the linear approximation farther away, basically. You're not even sure that's where you're going to move. The error will compound, right? So error compounds as you move farther and farther away from where you start off with. And that's why you don't take a gazillion steps, but only 5 or 10 or whatever.
So can you run the model predictive control, run the LQR problem at every time step in parallel?
Yeah, there are gazillion heuristics you can do. I mean, you can run in parallel, you can do many iterations and increase the accuracy and so on. In my opinion, there are books about how to do this well, and it's very widely used, as I said. It's a very good heuristic. Again, for nonlinear, we don't have anything provable, but it's hard to prove anything about it anyway. But look at the problem we solved. It's actually an interesting observation. We solved a very hard problem. Not stabilizability or controllability or some kind of niche. No, control, optimal control of a dynamical system, which is a hard problem. And on next Tuesday, we're going to start on an even harder problem, which is how to predict the output of a complicated nonlinear dynamical system. More questions? See you Tuesday.